We fit bitmaps to limited memory. We did color compression, as you mentioned. We did hardware that can follow the CRT theme, which is the coprocessor. We did the bit blitzing stuff inspired by the Lisa and the Alto. And we did 8 reusable sprite engines. I'll talk about all of these in more detail later. So, the coprocessor. All right. We had learned, as I mentioned, that the designers for the VCS did all kinds of impressive things because they were following the beam down the screen and they would make a lot of changes on the fly. And so in our second system, the Atari computer, we put in the ASIC, something that did a DMA display list. So it would follow the screen and it could conceivably change modes on the fly. It could turn on vertical and horizontal scrolling on and off on the fly, turn on and do some other things. But it did this on a sets of lines basis. It knew about vertical, it didn't know about horizontal. But we made that transition. So it executed a display list. It could also trigger an interrupt, and the interrupt could come in and change palette registers or horizontally reposition things, stuff like that. So the Agnes is an order of magnitude more powerful machine, which we'll talk about more shortly. It can wait for a given beam position, horizontally or vertically, and make changes right there. And the changes it can make are not only to itself, it can actually move stuff from any place in memory, anywhere into any of the chips. It can change colors, it can change positions, it can initiate blitter operations. Imagine I had a section of the screen that had been rendered and was stable, and now that it's been displayed, then I used the coprocessor to start a blitter operation to start changing that memory now that it's been displayed, because another piece is going to be displayed, right? So I can double buffer within a frame.
The copper could move a block of memory from DRAM to registers in any of these 3 chips. It was very generalized.
So, for example, the bit blitter is in this system, so we can run things back in there. This thing is video I/O, so I can change palette registers here. Maybe I want to do something to or from the non-video I/O. It can hit something out here. On the fly, without needing to be supervised by the main process or processes that are running in the Amiga OS. These are some examples, right? So, all right, bitmap hardware. Of course, when we did the Atari DCS, memory was way too expensive to have a bitmap at all. The Atari personal computer had a bitmap, and it had a lot of functionality, as I described, to make it more flexible. We were always thinking about how much resolution we could afford to cover and how to do it. We decided to go as far as we could go with standard TV timing. So we could do 320 or 640 pixels across. Now on a monitor you can do that. On a TV you can't do that exactly. You can build things that are modulated with that resolution, but the bits have to be more than 1 pixel wide, otherwise they're going to fall into the color clock and do all kinds of funny artifacts instead. All right? And vertically, if you don't interlace, you can do up to 240 lines vertically, but if you interlace, you can do, in principle, 480 lines. And the Amiga was set up to do that under some circumstances, because it could align and could even be recorded. We were thinking about building several different machines, and the lowest level one would be a pure game console. And we were thinking about using 16K bit DRAMs. So it would be 32K bytes, 16K words. What can you do in that? And so we were thinking, well, okay, maybe we have room for some program, and we have some room for bitmap display, and we have room for anything else in there. I have another slide where I'll talk about what those costs are. So to be very flexible, we could make a monochrome display. We could make stack displays up to 6 bits in parallel. So we could have 64 different colors. What they would do is actually point to a whole bunch of different palette registers. Each palette register is 12 bits. Each palette register had 4 bits for color, 4 bits for chroma, which is the where the color is, how intense the color is, and then the plain luminance. We then added an extra mode where if you've got a palette register covered, you can switch and hold 2 of those 3 values and smoothly modify the third one. So the Amiga could do shading effects that you couldn't do with an ordinary personal computer or video game doll. Why? Go ahead.
Oh, I also wanted to add, some people might ask, why only 6 bits per pixel? You know, why not more? In engineering, you're always up against constraints. And I was the keeper of the budget of how many transistors fit inside one of these chips and also the number of pins. And so even though we discussed, you know, more resolution, when I went to my budget part, it turned out that we ran out of pins.
Yep.
That is one of the architectural constraints that we had to deal with.
And finally, we had learned the Atari VCS was demonstrating vertical scrolling, for example, because the firmware controlled it. And so we built hardware-controlled horizontal and vertical scrolling in the Atari computer, and we continued that process here. And this is just a little bit of the detail. If I do 320 by 240 vertical, non-interlace, right? 1 color. I can fit that into just under 10,000 bytes. The Atari video computer had 128 bytes. Not K bytes, not 10K bytes. Had 128 bytes. The first Atari personal computer had 8K bytes total for everything. We were thinking about building a machine where the minimum system would have 32K bytes. So with just 1 color, we would use a third of the memory right away. If we built a 3-plane system, so it's got 8 different colors, that's going to cost us most of the 32K byte design right away. And we're thinking, how much money are people willing to pay for a machine that can render colors? We did a split system, so we could take 2 or 3 bit planes as the background, and 2 or 3 more planes that could move independently, and we could do our bit splitting of complex objects in one of them. And then we could switch the priorities so that the things move behind the trees or in front of the clouds or however the game was going to work. For a high res, if we were going to go drive a monitor for 640 by 480, that's going to take most of the 128K bytes that we actually shipped in the first Amiga computer, the Amiga 1000.
To demonstrate what could be done, I had actually written some bitblit routines in 6502 assembly and fork, if you can believe it, on an Apple II, just as a learning project while I was at Apple. But that turned out to be valuable because I could bring something over to Jay and demonstrate it.
So imagine we have a background. It's got some number of bits of depth. And we've got the graphics of a character, an avatar. And then we've got something which is the outline of that character. So what the BitBlitter can do in the time it takes to read and write it into memory is it can grab the graphics of the Smurf, it can grab the outline of the Smurf, it can grab the background, and can cut and splice them together and stick them back in the same memory or in different memory. And again, in the time it takes to read it and write it.
So one of the ideas that Jay and I came up with was to just make the blit logic completely flexible. It turns out that we reinvented what nowadays would be called a 3-input lookup table in an FPGA, and that became the ALU for the blitter, which allowed it to do basically any function of 3 variables, again allowing more flexibility for the software people to do crazy things.